Hello, everyone, and welcome to our presentation called DVT prevention device. DVT, or deep vein thrombosis, is a serious medical condition that affects up to 900,000 people annually. This occurs when a blood clot forms in a vein, leaving individuals susceptible to short-term complications such as pulmonary embolisms. COVID-19 has exacerbated the risks of DVT for hospitalized patients, many of whom are immobilized after operation. As such, this project proposes to design an unobtrusive and affordable device meant to reduce the number of deaths. Specifically, the goal will be to design a wearable device that censors the user's movements and actuates accordingly to lower DVT risks.
Mechanical prophylaxis solutions shown here are widely utilized in combination with blood thinners to increase blood flow and prevent DVT, especially in hospitalized patients. However, these devices all immobilize the patient, are painful and uncomfortable, and thus lead to low patient compliance rates, as low as 55%. Our solution is the DVT prevention device, Dvt-Pd, a wearable, portable, smart actuation device for DVT risk mitigation designed for ambulatory surgical patients. The system housing can be rotated around the leg depending on patient positions. The electrode pads for actuation are weaved into the sleeve, which is made of one-size nylon fabric. DVT mitigation devices exist, but Dvt-Pd is a portable and self-contained. B uses a closed-loop system that smart senses and actuates on ambulatory subjects. C can be dynamically configured based on subject state, and D provides higher increase in blood flow speed and patient comfortability. Dvt-Pd is worn around the calf. It's unobtrusive and designed to sense the user's movements. Once the machine learning model determines that the actuation criteria are met, Dvt-Pd gives a vibration warning and actuates via neuromuscular stimulation through the electrodes on the gastrocnemius muscle to promote blood flow.
This is the control system diagram that illustrates how Dvt-Pd operates. There are two different modes of operation, sensing and constant actuation mode. In constant actuation mode, Dvt-Pd will be constantly actuating to increase the blood flow during surgery. In sensing mode, Dvt-Pd will be sensing the patient's movements, classify their activity, and then determine whether or not actuation is needed. This shows Dvt-Pd sensing schematic and components. The sensor is the ADXL 345 accelerometer, which is reading the X, Y, and Z positional data of the patient. This sensor is very small and does not consume a lot of power and is powered by a 3.7 volt lithium ion battery connected to the microcontroller. This illustrates how some of the positional data was collected with the accelerometer. Positional data will be collected from recovering ambulatory patients in positions of interest, which include them laying down, sitting, standing, walking, and a few patient bedside exercises, which naturally increase the patient's blood flow.
Here's an overview of our overall system. The sensing system, which consists of an accelerometer, will sense positional data and send it to our web server for processing via an HTTP request. This data is then fed into our machine learning model that classifies it into 4 activity classes, which will be processed by our actuation algorithm and determines whether actuation is needed. Our machine learning model was built using the TensorFlow Python library. We evaluated several machine learning models considering both the runtime and accuracy. After testing these different models on synthetic data, the single layer feed-forward network performed the best in terms of accuracy and was chosen as our current machine learning model. We generated synthetic data representing activities distributed between lying down, sitting, and standing as seen on the left. We then performed data processing that included equalizing and normalizing our data, fed it into our ML model, and achieved an accuracy of 86.7%. This is very promising and hope to conduct an actual study when our IRB approval comes in.
Nmes is a type of electrical muscle stimulation that will be applied to each gastrocnemius of the patient. When the stimulation is applied, the muscle will contract and act as a muscle pump. This is shown to increase the blood flow velocity in the deep veins by up to 400% compared to the resting blood flow velocity. These pictures show the electro replacement that will be coming from the Nmes circuit. The signal will be flowing from the anode through the skin to the muscle tissue and then return through the cathode. The distance between the electrodes can affect the intensity needed from the Nmes circuit, and it is important to consider in order to maximize patient compliance. NI Multisim was used to simulate the Nmes schematic circuit. There were 2 parts to the schematic, the timing circuit and the DC to DC boost converter. The boost converter is used to boost the microcontroller's output voltage up to the desired 25 volts, while the timing circuit was used to obtain a frequency of 30 hertz and a pulse width of 320 microseconds. The Butterfly IQ is a portable ultrasonic Doppler device that will be used to measure the blood flow velocity in the deep veins. The image on the left shows the expected blood flow velocity of a patient at rest, while the image on the right shows the expected blood flow characteristics of a patient during actuation with Nmes. The brighter colors show an increase in the blood flow velocity.
So after all is said and done, the main question that may be across your minds is how much does this cost? As you can see in the budget chart, our expenses were divided into 3 sections. Proof of concept included components that help with collecting results such as the Butterfly device and Nmes device. Based on the hardware resources, fabric materials, and stimulation components, we expect the cost for our device to be around $80. On the other hand, it's important to also consider the environmental impact Dvt-Pd will have. As outlined in numbers 1 through 4 respectively, our design will include a comfortable recyclable nylon fabric for the sleeve, a safe ABS plastic 3D printing material for the housing, rechargeable batteries, as well as latex-free electrode pads for stimulation. But arguably the most important considerations deal with safety and ethics. So we will need to ensure that the device will be lightweight and unobtrusive because it will be worn by patients of various ages and conditions, and we want to ensure there's no risk when putting on the device and actuating. Given that this will be classified as a Class 2 medical device and human data will be collected, the group has done IRB training and is in the process of getting approval. Looking into the future, we hope the design will continue to act as a reliable device that will reduce DVT risk and help patients of all conditions. Current DVT preventative products on the market lack that effectiveness to minimize DVT risk, which is why future research will be conducted so that one day Dvt-Pd may become a standard assistive technology option in the medical setting.